Okay, so we've all stared at this chart, right? Probably in some high school chemistry class, thinking it was just a big color-coded list of stuff to memorize. But what if I told you it's not a list at all? It's a story. It's a story about cosmic order, about this incredible, elegant design, and, my favorite part, some truly mind-bending hidden connections. So today, let's actually read that story together.
Yeah, you've seen it a million times. But do you know what's really going on here? This isn't just a chart. It's a code. It's a secret key that unlocks the fundamental behavior of literally everything in our universe, from the air you're breathing right now to the most distant stars. And you know what? We're going to crack that code.
So, first things first, where does this beautiful structure even come from? It's not just some convenient filing system that scientists made up. Nope. The whole thing is built on a deep, universal principle. Think of it like a cosmic symphony, with this specific rhythm that all matter in the universe has to follow. And that rhythm, it's called the periodic law. Now that sounds a little intimidating, but the idea is actually super simple. It just means that if you line up the elements by their atomic number, how many protons they have, their properties start to repeat in these predictable patterns, kind of like the waves you see here. It's this repeating cycle that's just woven right into the fabric of reality. And that's the genius of the periodic table. It takes that invisible, abstract law, that cosmic rhythm, and makes it visible. This whole arrangement is designed to bring that repeating symphony of the elements to life right in front of us. It's absolutely brilliant. Okay, so we know the why behind the design. Now, let's get our hands dirty and figure out how to actually read this thing. Think of it like a map, and we're going to start with the two most basic directions, going across and going down. First up, let's look at the horizontal rows. We call these periods, and a good way to think about them is like a journey. You start your journey way over on the left with something like lithium, a super reactive metal, and by the time you get to the end of the row on the far right, you've arrived at something like neon, a totally chilled out non-reactive gas. It's this smooth, predictable change, and it happens in every single row. Now for the vertical columns. These are called groups, and this right here is where the table's magic really starts to shine. The number one rule is incredibly powerful. Elements in the same column act alike. They have similar chemical personalities. And the reason why is so simple, it's profound. They all have the same number of electrons in their outermost shell. That's it. And because of that simple rule, you get these chemical families. Take group 1, the alkali metals. They're all so ridiculously reactive, they'll literally burst into flames in water. But then you have group 18, the noble gases, and they're so stable and aloof, they barely interact with anything at all. Same column, same family vibe. So we've got the basic grid of our map, the rows and columns, but now we're going to zoom in. We're going to look at the major land masses, the continents of this elemental map, and some of the hidden currents that flow between them. You see, the table is also split into these 4 distinct regions, called blocks. You can think of them as continents. And just in case you were curious, those letters S, P, D, and F, they actually refer to the shapes of electron orbitals. It's just another hidden layer of order that defines the unique character of each of these elemental continents. And here's a quick tour of those continents. You've got the S block, way over here on the left, that's groups 1 and 2, then the P block, all the way on the right. In between, you have this big valley of the D block metals. And then, kind of floating down at the bottom, you've got the F block. Each one has its own unique properties. So, why does all this structure matter? Well, because this is what makes the periodic table so incredibly powerful. It's not just a list, it's a predictive tool. This whole setup creates predictable patterns or trends in things like atomic size or a property called electronegativity, which is basically just how badly an atom wants to snatch electrons from other atoms. It lets us guess how an element will behave before we even run the experiment. So we've got it all figured out, right? We have the vertical rule for groups, the horizontal rule for periods. Everything seems so neat, so tidy, so predictable. But what if I told you there's another pattern hiding in plain sight? A pattern that actually breaks those very rules? And that brings us to the final and, I think, most fascinating part of our journey. We're about to uncover a really surprising connection that operates completely outside of the simple up and down, left and right logic we just learned. Okay, check this out. This is where things get weird, in a good way. We're no longer moving just up and down or side to side. We're moving diagonally. And when you do that, this subtle hidden connection pops up between elements you would never, ever expect to be related, like lithium and magnesium right here. This strange phenomenon is called the diagonal relationship. And what makes it so cool is that it completely breaks the main rule we just learned. It connects elements that are not in the same group. According to the rules, they shouldn't have similar properties, and yet they do.
And this isn't just some one-off fluke either. As you can see, this effect is strongest between these three specific pairs up in the corner of the table: lithium and magnesium, beryllium and aluminum, and boron and silicon. There is definitely a pattern here. It just doesn't follow the rules we thought we knew.
So what is going on here? Is this just some cosmic coincidence? Absolutely not. It's actually a perfect balancing act. See, as you move across the table, atoms get greedier for electrons. But as you move down the table, they get less greedy. Well, when you move diagonally, those two opposing forces almost perfectly cancel each other out. The results? They end up with a similar size and a similar charge density. Let's use our lithium and magnesium example to make this crystal clear. If you move down from lithium, the atoms get bigger. If you move across from lithium, they get smaller. But if you move diagonally from lithium to magnesium, those two opposing effects, the push to get bigger and the pull to get smaller, they basically cancel out. And this is a huge deal. It's why lithium actually behaves more like magnesium in things like batteries and alloys than it does like sodium, which is in its own family.
Which really brings us to this final thought. We started with what looked like a simple grid of boxes. We peeled back layers of structure, periods, groups, continents, and then we found this beautiful hidden connection that actually breaks the simple rules. The periodic table isn't just some static chart on a classroom wall. It's a dynamic, living map of the relationships that govern our universe. And it's just full of insights for anyone who takes the time to learn its language. And that makes you wonder, what other hidden connections are still waiting in there to be found?